I'm Roland Minton. These are some of my favorite math stories. In this episode, mathematics is routine. We will look at the traveling salesman problem. The name is out of date, but the problem is a modern, everyday, multi-million-dollar concern for industry. Mathematically, it has the interesting property of having a known solution technique that is completely impractical. Finding a technique that quickly comes close to the solution can save a company millions of dollars. The traveling salesman problem, usually used TSP as abbreviation, centers on a salesman who will make calls on multiple clients and then return home. A small example would involve visiting 3 clients located at A, B, and C. The following graph indicates the cost of going from site to site. To start with, let's say the numbers represent the number of miles between sites. So from home H to site A is 20 miles, from A to B is 28 miles, and so on. The salesman wants to sequence the trip to meet with each client while traveling the fewest total miles. Before solving this problem, note that the numbers could also represent time or expense or any other quantity that the salesman might want to minimize. Also, the idea of a salesman making physical visits is outdated, but deliveries to locations of packages or food are everyday problems for delivery companies. How can the TSP be solved? Well, this is easy. List all of the possible routes, find the cheapest one. In the first route listed below, the delivery starts at H, drops off a package at 8, cost of 20, moves on to B, cost of 28, then to C, cost 34, back to H, cost 31. Adding them up, total cost is 113. A second route goes from H to A to C to B to H. Adding up those numbers, cost is 109. A third route is starting from H to B to A to C back to H. That cost is 114. There are 3 more routes. One is H, C, B, A, H, but this is route 1 in the opposite direction. In this problem, our cost doesn't depend on which direction is traveled, so we would still get that cost of 113. Similarly, HBCAH repeats route 2 backwards and is the smallest cost in the best route. HCABH repeats route 3 backwards. So the cost could depend on direction. For example, if there are one-way streets, the route from A to B might be different than the route from B to A. In this case, we would have listed all 6 routes and all 6 total costs. So this was not very hard or very interesting. Delivery trucks, of course, make more than 3 deliveries at a time. How many routes would we have to list if there were 10 packages to deliver? Let's go back to our simple example, which had 6 total routes, 3 of which were duplicates. To compute this, we use an area of math called combinatorics, which develops clever rules for counting. Here we look at how many choices are available at each stage. At the beginning, we choose one of 3 locations to go to first. From there, we have a choice of 2 remaining sites. After picking the first 2 sites, we must then go to the remaining site and return home. In all, we have 3 times 2 times 1, which is the 6 choices. And then we divide by 2 to remove the duplicates. Since this pattern shows up often, we give it a name. It's the factorial, and the notation 3 exclamation mark. If we have 5 deliveries to make, there would be 5 factorial, 5 times 4 times 3 times 2 times 1, which is 120, divided by 2, or 60 routes. For 10 packages, there are 10 factorial divided by 2 routes. I want you to guess how large this might be. 3 packages had 3 routes. 5 packages produced 60 routes. Do you think 10 will put the number over 1,000? If you say over, you're right, but it's not just a little bit over. The answer after dividing by 2 is 1,814,400, where this time the exclamation point means surprising. This is why the solution technique of listing all possibilities, exhausting all of the possibilities, it's called the method of exhaustion, is impractical. The factorial, the number of routes to consider, grows at an incredibly fast rate. A brief sidetrack will emphasize this. A common question in mathematics competition is to compute the number of zeros in a factorial. We'll do 100 factorial as an example. It's a nice little combinatorics problem. So how do zeros get produced? Multiplying by 10, or 20, will tack a 0 onto the end. There are 10 of those numbers in 100 factorial, 10, 20, all the way out to 100. Also, a 5 times a 2 will make 10. Each set of 10 numbers has multiple 2's, but only one 5, so there are 10 more zeros to add, 5 times 2, 15 times 12, and so on. That's 20 zeros. We're missing some. Can you see why? Well, multiplying by 100 will add 2 zeros, and 25, 50, and 75 have 2 factors of 5, and so they'll also add 2 zeros. Including the 4 double zero multipliers with the previous 20 gives us 24 zeros. If that doesn't show you how incredibly large 100 factorial is, maybe this will help. In front of the 24 zeros are 135 more digits. For a reasonably large number of deliveries, then, even a fast computer would need a few decades to compute all of the possible routes. In our first simple example, all of the costs were about the same. Would saving 4 miles really make much difference? If an algorithm could quickly identify a very good TSP route, time and money could be saved. What might such an algorithm look like? We'll try two, neither of which is very good. They are both examples of what are called greedy algorithms, where we greedily grab the best options at the beginning. This turns out to be a short-sighted approach that can force us to be stuck with terrible options at the end. In our simple example, we start at H. Which of the 3 sites is closest? Well, site A is only 20 miles away, so we go there first. From A, is it easier to get to B or C? From A to B is only 28 miles, so we go there next. We now have to go to site C and back to H, even if those are horribly expensive. The route produced by this, called the nearest neighbor algorithm for obvious reasons, is HABCH, whose total cost of 113 is not the best. Another way to go is more indirect. Which is the absolute cheapest step? H to A at 20 is the cheapest, so let's include that. What's the next cheapest? H to B is 22, so let's include that as well. But what choices do we have left? We start at H, go to A, and then to use H to B, we're going to finish at B and return to H. That leaves C in the middle, so we add in AC and CB, which actually are the 2 most expensive legs on the map. The route is HACBH, which does actually happen to be the optimal route. However, notice that if A to C and or C to B had been more expensive, this would not have been ideal. A lot of research goes into finding excellent TSP routes quickly, since delivery companies must design thousands of multiple site delivery routes each day. On a less practical note, some researchers have applied TSP techniques to artistic goals. The following graphic was created by Robert Bosch and is taken from his University of Waterloo site. It's a TSP route connecting 100,000 pixel sites. That's pretty cool. Maybe that's why she's smiling.